Thank the organizer for the invitation to speak at this nice conference. So we'll talk about thermalization and its relation with extended concepts of locality, like pseudolocality, in quantum systems. So we've heard about thermalization quite a lot, and so the main protocol, the kind of type of situation I'm looking at, is like this. So we start with some initial state, whatever initial state, you can think of it as a pure state, mixed state, or whatever, in some very big system, and I will do everything in arbitrary dimension. You can think of a quantum chain or a lattice of any dimension, regular lattice of any dimension. And then you do some time evolution on this initial state, okay, with some Hamiltonian H, which finite range interaction, okay, for a very long time. And then the question is, if you do this for a very long time, you observe locally, so we'll say reduced density matrix or something around some region, will you see some thermal state emerging? Okay, so that's the question of thermalization. Okay? And so the results that I would like to present some rigorous results within this problem. Okay, so giving some answers to these problems, which connect this question to the presence of conserved charges, in particular local or quasi-local or pseudo-local conserved charges. Okay, so that's the main situation I'm looking into. So with some equations, basically, we have some lattice, lambda, regular lattice. I'm thinking of it as a cubic lattice, dimension d, size L, and on each side some finite dimensional space, say c to the n. Okay, and we start with some state. Okay, and I will think of the state as functionals on observables. Okay, so take the average of these observables. Given a state, you have a number. Okay, that's the state. And you time evolve with some Hamiltonian, so you can also think as something acting on observables, with e to the IHT and e to the minus IHT. Okay? So this is the main initial state and the time evolution. And then we look for what happens at large time. Does it go to a thermal state? So a thermal state, we know how to describe these things: trace exponential minus beta h, etc. Okay? Now, of course, if you do this in finite systems, finite number of sites, certainly there will not be thermalization because there will be quantum recurrence. Okay? You can still ask the question about thermalization in finite closed systems. You can ask after a large time, will it get close? Will local density matrices get close to some thermal density matrix or some density matrix which is reduced from a thermal state of a large system? Okay? So you can ask how close it gets to some thermal state in finite system. Okay? And the larger the system is, the closer it will get to some thermal state. You can ask also, maybe in a simpler fashion, take the infinite volume limit, and then you can ask really the question, at infinite time after having taken the infinite volume limit, will you get to a thermal state, an exact thermal state? So the large time limit, does it exist? And you get the exact thermal state. Okay? So this is what I'm taking. So take the thermodynamic limit first. L very large, so you have a very large system, and you notice that when I use a state as a vector in a Hilbert space, taking the large volume limit is a bit tricky, but if I use a state as a functional on local observables, then it's fine. Okay, so this is better notation like that. Okay, so take the thermodynamic limit, and then suppose that, well, one question is, does a large time limit exist? Okay, limit t goes to infinity of the state of a time evolved local observable. Does that limit exist? If it does, this is equilibration. Okay? And this is what people will refer to as equilibration. And if it exists, is that limit described by some thermal state? Large volume limit of a thermal state. Okay? That would be thermalization. So these are questions that I'm looking into. In fact, I'm interested in more the second question. So if the large time limit exists, do you have thermalization or not? Okay. Yeah. Okay, so these are the questions. There are, so many people, of course, have looked at this kind of situation. Okay? In particular, in the context of quenches, people have looked at, start with some ground state of some Hamiltonian, change the parameter of the Hamiltonian, let the whole thing evolve and see what happens last time. Okay? People have looked at thermalization also in different contexts and quenches. You can start with some thermal state or some other density matrices. There's a lot of reviews on that. There's a lot of nice results. And the results I will talk about are mostly my results, but I will cite some other rigorous results in this area. Okay? So any questions about this? So that's the situation. Now, there are, before I come to my results, there are a lot of concepts that have being studied or being proposed within this set of problems. Okay? And one of them is the eigenstate thermalization hypothesis, which you most likely have heard about. Okay? What's the eigenstate thermalization hypothesis? Well, depending on what you read or who you hear, there are many versions of it. So, mainly I know kind of two versions. One version, say a weaker one, it says that if you are in an eigenstate of a Hamiltonian, local Hamiltonian in a very large system, and calculate the average of a local observable, then this average does not depend very much on the details of this eigenstate. It just depends on the eigenvalue of the Hamiltonian. Okay, so this is an eigenstate, just depends on this eigenvalue. That's kind of doesn't depend very much on all the details. That's kind of the first bit here. Okay? Now, fortunately, that first bit is not super precise because this eigenstate thermalization hypothesis is supposed to work in non-integrable systems, because if you have integrable systems, you have some generalization of that, and I'll come to this. And in non-integrable system, usually you expect to have non-degenerate energy eigenstates, and so of course, an eigenstate then is completely characterized by the energy eigenvalue. Okay? So it's not very a big statement. The kind of more accurate statement is that these average of local observables in energy eigenstates should be smooth function of the energy eigenvalue. So it should not vary very much when you change the energy eigenvalue a lot. Okay? In fact, there's another problem with that. This is a very large system, so these energy eigenvalues will be large. So actually, you've got to look at average of energy density. And then the average, so the statement, kind of a more precise statement of it, would be that if you take a sequence of energy eigenstates in growing lattices, so a sequence of energy eigenstates, so you take your Hamiltonian, which is homogeneous everywhere, except for in the boundary, you set the boundary in some way, which I'm not going into the detail, and if you take the lattice bigger and bigger and bigger, and you make sure that the sequence of energy eigenstates is such that the limit of the energy density converges to some value, then the limit of any other local observables will also converge to a function that just depends on this energy density, and of course the observable. That would be a statement of eigenstate thermalization hypothesis, this kind of dependence on energy density. And it will be a smooth function of this energy density. Okay, so that's kind of a weak version, if you wish, of eigenstate thermalization hypothesis. A stronger version, which I think, if I know I don't know exactly where it was proposed. Probably even in the initial paper by Jensen and Sharkar was also proposed there. Was certainly in the later paper by Rigaud and et al. The stronger version is that actually this function there is nothing else but a thermal average. Okay? So large volume limit of thermal average. Yes?
Would you be thinking of adding like a constraint on what happens at the corners of the spectrum? Because then at the very low and high ends it's not expected to be valid, but somewhere in the bound?
Well, yeah, so I don't know. That's my answer. And probably this is too wide a statement. So you probably would have to add constraints to have something that is more precise. I agree. Okay. But as far as I know, there's no proof of eigenstate thermalization hypothesis with any additional constraint or not. So this is kind of the idea, but yeah, most likely one will have to add constraints. Other questions?
Will you discuss the off-diagonal matrix elements of the operator? Because it might be important for the...
It might be possible, but I will not discuss. Yeah.
Sometimes it's emphasized that it's also necessary.
Sometimes, yeah, for in this context as well. That's correct. Yeah. But so there it is. There are many other constraints and things you might have to say for this whole thing to work. And as of now, well, it's not completely clear what is exactly what is it you will have to say for everything to work. Yeah.
Second statement isn't just equivalence between microcanonical and canonical.
Yes. Basically, with the second statement, it's saying that you can take one state and represent your whole thermostat. Okay? And yes, indeed, this is something that people have used in the past as well. So the second statement is not necessarily that much stronger, right? Yeah. Other questions? Okay, so if this is the case, well, then this helps in the here there's no dynamics, by the way, and it's just take an eigenstate. Well, of course, if you start with some state and evolve for a large time, if the limit exists, you may think that you can then describe this limit, which would be stationary if it exists. You can describe this limit using the eigenstate of the evolution Hamiltonian. Okay, and then if you go into the details and add more details, you will conclude that the ETH will allow you to show that if thermalization occurs, then if equilibration occurs, then there's thermalization. Okay, so that's one possible application of ETH. Okay? So that's one of the ideas that came out, as was mentioned by many people. There are a lot of details around that, which will be important to kind of decipher, to make these ideas more precise. Okay? It's not so easy to make all this more precise. Okay, but it's something that allows you to understand a bit of thermalization. Another concept that has been coming out in this context is, well, basically the idea of if you have more conserved charges than just the Hamiltonian, well, the whole thing should be generalized, of course. Okay? And in particular, if you have many, or say infinitely many conserved charges, Hamiltonian and a lot of other, say, local conserved charges, like an integrable system, what should generalize this type of thing? Well, what should generalize this is something where you have not trace exponential minus beta h, but exponential minus sum over all these local conserved charges with various chemical potential. Okay? This type of thing actually is the basis of the quantity action formalism of Jean-Sébastien Fabian, if I'm correct, where they actually indeed construct a state psi which should represent that trace at large volume. Okay? And this type of ratio of traces is something that is referred to as generalized Gibbs ensemble. Okay? It's like a Gibbs ensemble, but generalized by putting infinitely many local conserved charges. It was, formally first written by James in 1957, who did consider the presence of many conserved charges to generalize what Gibbs had done. It was based on entropy principles, but really discussed and mentioned as a generalized Gibbs ensemble, something that can occur in large time evolution by Regal et al. 2006-2007. Okay.
Yes, just one other comment. I mean, here, I don't want you to give the wrong impression that we were doing GGE. So I mean, essentially we showed convergence of the approach using overlaps to GE, at least under reasonable assumptions.
Yes.
But of course, GGE is credited to many others, but certainly.
Yeah, certainly. Yes. Okay. So what Jean-Sébastien said is that they did not invent GGE, but other people did. More or less.
I don't know.
But exactly. So this, I mean, a lot of people.
You see, Alessandro just asked me why we're cited there. I mean, we don't deserve to be cited there at all.
As a matter of fact, I disagree.
I don't know.
The generalized microcanonical ensemble is a byproduct of the transaction approach, and
absolutely,
that's that line.
It pertains more to
that's how I understood the paper.
You understood correctly.
And better than all the others.
Or the previous slide than this one.
Okay. So, GGE then. GGE. Of course, a lot of people have studied GGE and the concept of generalized thermalization. You start with a state, you evolve with an integrable Hamiltonian, do you get a GGE? And there's a lot of work, and I will not cite all of the work, and a lot of people in this room have done work on that. So I apologize for not writing your name, but I write kind of some initial names of people who did initial work, and then there's like 10 years, which I passed very fast, coming to that paper, 2015. And what this paper did, I mean, really based on a lot of works of a lot of people before, is to say that, or to show, at least numerically, with quite some precision, that actually this GGE requires a bit of a further generalization. These local conserved charges are not enough to describe the resulting state, large time stationary state. When you start, depending on the initial condition, sometimes they are not enough. So you start with some initial condition, do a large time evolution with an integrable Hamiltonian. What you get is not a GGE as initially proposed by Regal et al. It's something that looks like it. But these HI, what you should put in there, is not just the local conserved charges of the integrable models, but you should put also the quasi-local conserved charges. Now, what are the quasi-local conserved charges? It's a very nice concept which really was developed by Lievsky and Prosen from 2013, 2016. In fact, based on concepts I think originally invented by Prosen in 1999 and 2000. Those are pseudolocal charges, which I'll come to it. And so what they found, so these quasi-local conserved charges were computed exactly in very, very nice works in Heisenberg chains So you can compute exactly using transfer matrix methods what they are. Then you can use them in using various like quantization formalism and some generalization of thermodynamic beta ansatz in order to check what happens at large time and indeed to show that they must be involved in these GGE in some integral models with some initial conditions. Okay? The GGE must include quasi-local conserved charges, not just local conserved charges. That's the kind of main strong statement of this last paper. Okay, any questions about that, comments, whatever? Well, very good. So the goal of the talk is actually to make some statements about all these concepts, especially about the GGE and the presence of local or quasi-local or even pseudo-local conserved charges, and to have some precise, rigorous statement about that. Okay? So the questions here that I'm asking is like that. So we say you should put quasi-local charges in this exponential there. That makes sense, and there's a way of making that more precise. In the end, you can take a finite volume limit, differentiate with respect to these beta, take the large volume limit of these derivatives. You get averages, which you can compare with averages in the original state. You can make some precise statement. Question, however, I have is if these HI are local or quasi-local or whatever they may be, but if you have an infinite number of them, what is this infinite sum? Is it still local? Well, most likely not. Is it still quasi-local? Maybe not. So what is it? Right. So this is not very precise. And if it can be anything, local, quasi-local, or whatever, it can be anything, then is there even any meaning to the GGE? If I can put any operator there, conserved, but not local, then I can put anything. Then it's the diagonal example. Okay? So it has no meaning. So that's one question. Okay? The other is, well, related to that, how do we fundamentally characterize this GGE density matrix? This is formal expression. What is it, more precisely? And then other question, of course, what are some general conditions for thermalization to occur or generalized thermalization to occur? Because there are some very nice rigorous results about conditions for thermalization to occur, some which are cited there. These are results mostly in finite systems where you prove that thermalization occurs with a lot of precision. The reduced density matrix become very near to thermal density matrix after a large time, and it is nearer if the system is larger and things like that. Okay?
Can I make an heretic comment from the experimental point of view? Don't you have to think about it? What can I make? What observations can I make? Because if I can make an experiment to measure many-body eigenstates, I will never ever see one of those ensembles. Right? I will have to put the diagonal ensemble in there. If I only can measure local observables, then I'll probably be happy with the local conserved quantity.
I don't know.
But that's my conjecture.
Well, I don't think so. No,
I can measure local quantities. I can also measure non-local quantities. Probably.
No. So here, look.
To make a clever experiment, I can measure non-local quantities.
No. But here the point is that if you put just local quantity here or local and quasi-local, that changes the averages of local quantities. It's not right. So this is, of course, here you take average of local quantities always. Okay? So A is always a local quantity. Okay? But the state depends on the BTI, and the state that you get, as we've shown that in this paper, is the wrong state if you just assume that these IHI are the local conserved charges. This is the wrong state, in the sense that it gives the wrong average of local observables. So there is, there's a true meaning in putting quasi-local charges there. Then you may say, can I, given a set of average of local observables, can I always reproduce this set by putting just local quantities there? I don't know. But it's not very physical. This is not the quantities that occur there. So, I don't know. Okay. My answer to that would be I don't know.
Let's see. So from the
actually, I don't think so.
From the stuff we have recently with everybody, it's clear also that to a given accuracy, you can truncate this even this generalized GG. Right?
Yes.
I'm going to put a handful of families of higher charges, and in each family I'm going to put 10 charges or something. Then each time I increase this truncation level, the accuracy goes down.
Yes.
So clearly you can truncate it before things become brutally non-local. So in a sense, it's all, we can just gentlemanly agree that it's called local physics.
So, okay. So you can truncate this sum. And and you truncate and you get more and more accurate results by this procedure where you determine this beta I using the initial state and all that.
Yeah, so then the question is kind of thrown back to Jörg. How accurately can you measure
Benjamin,
something?
And I have always put. I have only put
okay, right. So let us keep.
resources in the experiment.
Let us keep this for further discussion afterwards.
Exponential number of students.
No. No.
Thank you. Good question. Let's discuss afterwards. Now, so, okay, in order to get precise results, there's a lot of nice mathematics, and of course I'm not an expert in this nice mathematics on these extended quantum systems, but I know a little bit of it, and there's a C-star algebra structure of it. It's not important for the talk, but it's just to say there is something precise that one can do about it. Okay, and you can use this structure and do theorems using using topological vector spaces, basically. Okay. So C-star algebra, so basically you take the set of local observables that are supported on finite number of sites. You can complete that. You get observables that are not necessarily supported on finite number of sites. It can be very large, but they still they have certain properties. In particular, they are finite norm, and so you can complete that with C-star algebra. So this contains this set of local observables, which is in fact dense in this C-star algebra. And there's of course a natural isomorphism, which is translation. Okay, so you can translate. This is a well-defined map from the point of view of C-star algebra. And the state is just a linear map from these observables, this algebra, to complex numbers, which is normalized, so that the identity has average 1. Okay. And then, given some local observable h, you can construct a Hamiltonian. So this, if you see it as a sum over all the lattice side of the translator of this h, then this is not a well-defined element of the C-star algebra. Nevertheless, you can construct this partial sum, and from the partial sum you can define time evolution and give states. Okay, so these kind of standard ways of defining time evolution and give states. Okay, so the Hamiltonian density kind of tells you everything. You can do time evolution, give state. You just have to construct partial sums of these Hamiltonian densities and then do limits, and these limits exist appropriately within the C-star algebra structure. Okay. Again, I see
you're going very fast all of a sudden.
because yes. Okay, I'm going very fast because I don't need, so I just want to say that there is a structure. Then when I say the theorem, you don't need that much of that. Okay, that's the idea. Yeah.
So if you now take a generic C-star algebra, so what do you mean now by trace?
So this is, I'm not taking a generic C-star. I'm not taking a generic C-star algebra. It is a particular C-star algebra, very particular structure.
Over finite dimensional vector space.
Yeah. So okay. So there are different ways of generality of how to describe it, but the basic way is take a sequence of C-star algebras of finite dimensional quantum lattices. Okay. You take the inductive limit.
You take a net of C-star algebras defined on lattices which contain each other. And for each lattice, you only consider tensor products of finite dimension.
Yes, exactly. So everything makes sense there, yeah. But then, of course, you can go to more general thing and all that. Okay, so there's this. Now, so what do we want? So I start with a re-thermalization theorem. Okay, so using that, you can say that if you start with something thermal, you evolve, you get something thermal at large time. Now, in this re-thermalization theorem and in the rest, there's one concept which is super important, is the concept of clustering. This clustering is just the fact that when you take observables in a state and make them very far from each other, then the state should factorize into product of the average of these observables. This is something that is true in Gibbs state. It can be proven in Gibbs states, and in higher D, this is at least for high enough temperature. And the concept of clustering that I'm taking is a very precise concept. There are many people have studied a lot of possible concepts of clusterings. Okay? And this is my own, but it implies a lot of those that have been studied. Okay? And my own is just saying that if you take state of a product of two observables minus the product of the average of these observables, absolute value, this is smaller than the distance to some power that's large enough, larger than the distance, larger than the dimension of the system, space dimension of the system. Okay? The distance is something that's well defined in the cubic lattice. For instance, the minimal number of steps you have to do for going from the support of the observable A to the support of the observable B. Okay? So that's a well defined notion in this quantum system. these double bar are just the norms. This is C-star algebra, so there's a norm. And then what I'm saying is that there's a coefficient that should, well, there's a number there in the coefficient, but this coefficient should not grow too much with, well, it should grow at most with the power, with the size of the observables. So the observables, they are supported on many sites, and the size is just how many sites they're supported on. And that coefficient should not grow too much. It should be a power a, so it doesn't grow too much. No. So that's a clustering property. Now, many clustering properties one can imagine. Okay, if this clustering property holds, in fact, independently of what this coefficient is, then one can easily show that the response functions are finite. So if you take the state of a of x times b minus the state of a times the state of b, sum of all of the x's, right, correlation function, right, connected correlation function, then this sum is finite. In fact, here I take symmetrized version of the whole thing because it's simpler for certain properties. So this is the anticommutator. Okay, so clustering, existence of response function. Okay, any questions on this? That's the first thing that's important. Okay?
So
now,
and why you call response function?
Response function because if you modify your state by putting an exponential of sum over x e of x with some coefficient there, and you differentiate with respect to that coefficient, and put that coefficient to 0, you get that.
Yeah, but it's response usually means something time dependent. It's quite uncommon name, but okay.
Response function, yeah. I was thinking of it as just response to a change of the. But it is true that response usually is time dependent. This is not time dependent. Yeah. Okay. Correlation function. Yeah. That's fine. Yeah. Very good. Yeah. Thank you.
Susceptibility.
Sorry. Susceptibility is how it's defined. Yeah. Thank you. Yeah. Susceptibility, of course. Yeah. Very good. Okay. So now Gibbs states have very nice properties. Okay. A lot of people have studied this Gibbs state from 1969, and the recent paper by Klisch, Gogolin, Castoriano, Riera, and Eisert, 2014, very strong results. And from these results, one is shown that Gibbs states actually have this clustering property that I showed. They are clustering. Okay, in fact, more than that, using results of time evolution by Lee and Bernsen, the fact that this slide counting and the rewriting of this time evolution by Gregory Hastings and Stratis, 2006, can show that not only Gibbs state, but a Gibbs state time evolve. So Gibbs state with respect to some Hamiltonian, time evolve with respect to another Hamiltonian, that this also satisfies the clustering property. Okay? That clustering property that I showed. Okay? So that is also true for in general for this thing. Now, this clustering property in higher D is not so obvious because, you know, in higher D you can have some classical critical point at some finite temperature. Okay? So certainly it should be true for high enough temperature. And that's the result of the theme of Eisert, that there is a universal number beta star, so some universal temperature, some temperature above which it is true that a clustering property holds. Okay? That's the result. Okay, so we have clustering property in Gibbs state, and you have existence of response function. Yes.
The statement is that above some temperature, all states satisfy this clustering?
Above some temperature, all Gibbs states of local Hamiltonian satisfy the clustering property. Yes, for any local Hamiltonian. So the temperature, beta star, depends on the Hamiltonian, of course. So given the Hamiltonian, yeah, some Hamiltonian density, can calculate some number out of that. So, you know,
and sorry, the measure of these Gibbs states relative to all states is?
With respect to all states.
Can I comment on that? In fact, it does not depend really, not even on the Hamiltonian. It only depends on the coupling strength, like the operator norm, the overall coupling strength, because, well, if you multiply the Hamiltonian by 5, then the number is changed by 5. And on the lattice animal constant of the lattice. So it's not even the dimension, but even less. It's very little properties you need.
Yeah, so here's the expert to that. Okay, so that's what we have. Okay, so these are nice results, and use it. Did you answer your question? Or will we talk afterwards?
Well, I was wondering if what sort of the entire Hilbert space, what sort of measure?
This I don't know. All I'm saying is, you know, take a Gibbs states, and this is a result about Gibbs states. I don't know about other states. Yeah. I wouldn't know how to characterize the measure. But okay, so given that, one can show a rethermalization theorem. It's not a very complicated theorem. There are 3 conditions, and it says the following: if your time-evolved Gibbs states are all sizably clustering, so this clustering property that I mentioned, in a uniform fashion, in some neighborhood of the segment between 0 and the temperature you're looking at. So you have to take a look at all temperatures from infinite temperature to some temperature. Take a complex neighborhood of that. Give states are also analytic. Take complex neighborhood and look at clustering property of that. Okay? That and its time evolved. Okay? And if this clustering property holds in a uniform fashion. Now, for finite time, this is true, it holds in uniform fashion. So the non-trivial bit of that condition is that this is true even for very, very large time. It is not obvious. Okay? So what you ask here is clustering hold even at large time. Okay? So if clustering hold even at large time, and
okay, so can I just ask? I mean, so you start with a Gibbs state of some local Hamiltonian, you time evolve with a different Hamiltonian.
Yes,
so
yes.
You do a quench.
And and
what you're saying is now basically initially you cluster and you have proved you always cluster.
Initially exactly.
But is there the cluster? Sorry, is this clustering allowed to grow with time? Like you would have expected, like
yes. This is the proof that I have is it grows with time. So the proof I have is not that it's not uniform in time. So if you go to large time, it doesn't cluster anymore. It's just finite time. Yeah, it's because it's Lycon thing. So you have I use this result Lycon and then exponentially decaying after that. Okay. So this is a non-trivial statement about existence of large time limit. And the other non-trivial statement then I can really call I call dynamical response function for some reason. So this is really the response function. Okay? So you sum over all x, substitutability, but you evolve time, so that these large time limit exists in C. Okay? That's the other statement, so the other condition. Okay? So these two conditions are like existence of large time limit. Okay? Two conditions. If existence of large time limit, and if this dynamics is something I call completely mixing, which I will come to right now. Basically, it means there's no other constant charges except the Hamiltonian itself. But I'll come to that. Then the resulting state, large time limit of the state exists and is a Gibbs state with respect to that evolution Hamiltonian. Okay? With a certain temperature, which one can write in some formal fashion. I don't have an explicit number for that, but there exists a temperature such that. Okay? So this is a rethermalization theorem. There are other rethermalization theorems which are thermalization theorems which are actually not so far from that. But here, what is interesting in this theorem is this condition, that this completely mixing condition, the fact that the evolution should not have other constant charges, and that I can make precise, and that's I think is rather interesting. How do you make that precise? What is the precise statement about not having other constant charges? Okay.
Sorry, Ben. Let me understand. You are proving that if you don't have other constant charges, everything thermalized.
Yes. For Gibbs, this is a Gibbs state. Right? You start with a Gibbs state, end up with a Gibbs state. This is a particular state, not any state.
It seems to contradict previous thought already.
I don't think so.
There is the condition C, which is probably
completely, yeah.
The condition C means that there is only one.
Is the one which changes the game.
The condition C means that there is only one invariant.
Yes, just the Hamiltonian. So, if you think about it, this is rather obvious, right?
This is exactly what that means. The completely mixing means it's only
the Hamiltonian is constant charge. Okay, so let me go to completely mixing.
Before in the answer field.
Let me go to the completely mixing condition, okay, and see what it does. So for completely mixing, I need the concept of pseudolocality, and that was invented as far as I know by Prof in 98-99, and then studied further by other people and led to that of quasi-locality. Okay. What is pseudolocality? So here's very simple. So suppose a pseudolocal charge, basically, is a limit of a sequence of observables on your lattice, quantum lattice. The sequence is a growing sequence, so Qn. It grows, so it is supported on larger and larger subsets. So the bowl is just all the sites which are at a distance n or below to the origin. So larger and larger subset, bowl of radius n. Okay. And you ask for a condition. The main condition is that the second cumulant of this charge diverge at most like the volume, so n to the power d, this dimension. Okay? So precisely, volume growth. There exists a gamma such that omega of, here I take anti-commutator, again for symmetry reason, q star q is smaller or equal than this gamma n to the d. Okay? So that's a condition of volume growth for all n greater than 0. There exists gamma. Right? Then you also ask that the limit action exists. So if you take omega of qn comma r, where r is local, any local observable, then you ask that this limit exists, the large n limit. Okay. non-trivial. And finally, you ask some kind of homogeneity. So translation variance is something, this is a precise statement, but basically this limit does not depend on x, and it does not depend on x in some kind of uniform fashion when you take the limit in large n. Okay? Three conditions. So this limit action is what I call pseudolocal charge. It's a linear space, and so that's a space that we consider.
The definition, which is
definition, yeah.
relative to omega.
To omega. So the space of pseudolocal charge is relative to omega. Okay. A subset of these pseudolocal charges are the local charges. You just take some, like the Hamiltonian, some overgrowing subset of some local thing. That you can see satisfies all the conditions. Right? And in fact, the limit action is just what is just the susceptibility equation. Right? That's the basic thing. Right? The quasi-local charges introduced by Yevsky and Prof in 2013, I believe, these also are examples of pseudolocal charges, but they have one condition, which is that the density have exponentially decaying tail, slightly stronger condition, but they are pseudolocal charges. Right? And these pseudolocal charges, quite surprisingly, actually satisfy a nice clustering property, which is a bit like a differentiation property. So Q, quasi-local charge, on BC, if you look at very large distance for the observable B and C, these are local observables. This is Q on B times omega of C plus omega of B times Q of C. It's like the derivative of BC equals blah, blah, it's like a derivative thing. Right? And this is true for any pseudo-local charge, so this is really a consequence of the volume law thing. Okay? It is easy to see that it's true for local charge that this holds. Because when you sum over all x's in your A of x, the sum of x which will be near to B, then you have the action on B, some of them which will be near to C, then you have the action of C, and then some which are far from everything, then you have no action. And here for all that, because it's essential that you have clustering property like the clustering that I showed previously. Okay? So these are the pseudolocal charges, they have these properties, and then completely missing, what is that? Completely missing is that the H should not possess pseudolocal charges which are conserved other than H itself. So more precisely, if you have a state which is stationary with respect to H, any state, any stationary state, so that satisfies this condition for all local observable. Okay? Well, the condition that the pseudolocal charge commute with H would simply be that this action, this Q action, on the commutator between the Hamiltonian and anything, be 0. Right? So if you have a stationary state, then Q being conserved would be that. Okay? Now, the definition of completely missing is that local Hamiltonian H completely missing if for every stationary state, the condition that this Q be conserved implies that it be proportional to H as a condition. Okay? So there, so in this way, you get to define what you mean by there's no other conserved charges that commute with Hamiltonian, but in a completely precise fashion. And notice that I never have to consider pseudolocal charges as operators on the space. They are just linear action on observables that depend on state. Okay? And that all makes sense. So I'm just considering their linear action. Okay? So that's the completely mixing thing. Okay? So if you work it out, it makes sense intuitively, but it is precisely stated. And from that you can prove reternalization. Okay? Questions? Well, that's correct. Does that
I'm
help?
a bit lost, but it's fine.
Yeah. But questions about where you lost in some particular? Yeah.
Why you need to connect this notion of conserved quantity to a state?
So it's a good question. So the point is that I define pseudolocal charges with respect to a state. It defines with respect to a state. If I change the state, I may have a completely different set. I don't know. Right? So if I want to say the Hamiltonian doesn't have any conserved charge other than itself, what I have to say, well, here I want to use pseudolocal charge. I want to say it doesn't have any conserved pseudolocal charge other than itself. But then the pseudolocal charge depends on the state. So I have to say, for every state, it does not have, the set of pseudolocal charge that I conserve the Hamiltonian is just Hamiltonian. But, for every state, it's not, that maybe that would be too much. And so what is sufficient to say is, for every state that is stationary with respect to the Hamiltonian, then the set of pseudolocal charge that commute with H, in that sense, is just Hamiltonian.
It is true that if it doesn't have any real conserved quantity, then it's completely missing.
That is true. So if you can prove independently that it doesn't have, then that will hold. That's kind of a bit weaker, if you wish.
So essentially, how do you define a concept quantity?
So here I never, you see, here there's no commutator between H and Q.
Yes.
Because I don't have an operator Q.
That's what was confused.
Okay. So I don't have an operator Q. Maybe I write on the board, I don't know if I have even time for that, but maybe that's worth it. So if I work out these equations, right? The first one says that omega, the state of H with anything, equals 0. So omega is invariant on the H translation. The second one is this Q blah blah, okay? So what is that? Well, this is omega of, there's an anti-commutator, but that doesn't matter. There's this Qn, and we're taking the limit of large n, right? Qn times H comma A equals 0. That's what I'm saying, the second thing. What is that? Well, since omega is stationary, that thing is more or less the same thing as H comma Qn times A. The fact that it's equal to 0 is basically the same that H commu with Qn. But I never say anywhere that H commu with Qn, all I see is in the limit and in the particular form. So that's how you connect with H commuting with this charge without ever introducing an operator. That's a solo charge.
That's a terrible question, but I mean, why not like H to the power of K?
H to the power, what do you mean?
The powers of Hamiltonian.
But it wouldn't be a quasi-local local charge.
But the fluctuations on of the charges, right? You just take the free algebra of the charges. Let me consider the fluctuation of the Hamiltonian. I also then need to define a state. This is quasi-local.
So, yeah. So I don't talk about fluctuation. This is just linear action. Set of out pseudo-local, quasi-local. If you have a constant charge and you know that some power of it given in a certain state is quasi-local, that will be part of that state, of that set. Okay, that's something else. Okay?
Yeah, but so what I'm saying is simply the fluctuations of all your charges are members of that set, right? And do they constitute the whole set?
Set, yeah. Think about that.
Can I necessarily think of a basis for this in terms of fluctuations or within the free algebra?
Well, not necessarily. I don't think so. I don't think so. But I don't know. This I don't know. To be honest, I haven't studied these fluctuations in terms of pseudolocality.
Because interestingly, you also need charges that are defined respective to a certain state.
Yes. Exactly. So indeed, so of course, then with respect to a certain state, you can do this control. So I don't. The answer is I don't know for that. Yeah. Think about this. Yeah.
You just said a moment ago that depending if you choose a different state, you get a different set of charges.
In principle, yeah.
But you think of omega really as coming from a stationary state of your Hamiltonian. So you're not. So if you would start out with a Gibbs ensemble, right, you would have like a superposition of all stationary states, and therefore you would get all these different charges together. Is that right? Or
yeah. So if you whatever state, if your state is some convex combination of given sample point, but that's a new state. Now it may have a different set of local charge. So when you take combination of such states, the set may change in a way that I don't know, haven't studied. Right? So it's every state will be.
So you would never start from a Gibbs thermal ensemble, because then you would have a superposition of all.
No, if you start with a Gibbs ensemble is a state. That's your thermal state, and this has its own set of pseudo-local charge given the Hamiltonian. Yeah.
Gibbs ensemble is just a linear combination of.
Yeah, sure. But so if you think of it in terms of linear combination, each linear combination is a linear combination of some states, eigenstate. Each of these eigenstates have their own set, and the Gibbs ensemble itself has its own set. And how these set of pseudo-local charges are related to each other, this I don't know.
Maybe you just.
But maybe yeah. Other questions? Yeah.
Can I ask if I give you a local Hamiltonian?
Yeah.
Can you tell me whether it's completely mixing? If I give you a local Hamiltonian and some initial density, can you tell me whether...
No, just like that, I don't know how to say that. So this is a formal condition. So
it's true with unit probability of random Hamiltonians and hard to prove.
Yeah, certainly. But this could be, investigated numerically. It is for precise state, you can investigate numerically. I don't know what best numerical techniques would be, this I don't know, but okay, other questions? Okay, so this is, what are the pseudo-local charges? Only those that are those that conserve is on basically only the Hamiltonian. That's the thing. Now, it would be nice to go to a larger family of states, and it turns out with pseudolocal charge you can construct a larger family of states. And here's the idea. Well, if you differentiate this exponential, you get exponential minus beta h, you get h exponential minus beta h. So if you differentiate with respect to beta, some thermal ensemble, some thermal state, what do you get? Nothing else but what I had called the response function, which is the susceptibility, of course, of h comma a. Okay? Which is, by definition, since h is local, is an application of this local charge, pseudo-local, defined with respect to that thermal state on A. That's what it is. Okay? So just a little computation, differentiating an exponential. Okay? It turns out that is the case. That's something you can see from the thermal state. You look, thermal state, that's correct. Okay? And so you can think of then of this equation as saying that this h is like a tangent vector at the point omega. Omega is like a point in some space of states. Okay? And the derivative with respect to some parameter of that point is a tangent vector on that point. Okay? So this is like a flow equation in some manifold of states. Flow equation. Okay? And you can think of this flow equation as connecting your thermal state by a set of tangent vector which are determined by quasi-pseudo-local charges, connecting it to the infinite temperature state. So you have some infinite temperature state. I write it here with a formula like that. It's a limit of some trace. Okay? You write a flow equation saying that the derivative with respect to some parameter is determined by some quasi-local, pseudo-local charge. And then you look at the state that occurs at some value of the parameter s equals 1 or beta equals something. Okay? And this set of states that are obtained as endpoint of pseudo-local flows is what I call the pseudo-local states. Okay? And Gibbs states are examples of that. Okay, show everything. Okay? Examples of that. Okay? Turns out, instead of taking derivative, it's kind of easier to integrate the whole thing. So you can integrate that. So precise definition, which I came up with, maybe it's not the best definition, but it works, is if you have a one parameter family of states which are all clustering, and with the omega 0 being just a trace state, the infinite temperature state, omega 1 being the state you're looking at, and you have a one parameter family of pseudo-local charge with respect to all of these omega s states. Okay? They are bounded. I'll come to what bounded means. Doesn't matter too much. And if s goes to qs is Lebesgue integrable, so you want to be able to do the integral, and omega s is related to all these qs in that way. So if you take the derivative of omega s, you get qs on it. Then we say omega is a pseudo-local state. Gibbs states are pseudo-local states. Turns out that, not only that, these pseudo-local states have a nice property on the time evolution. If you start with a pseudo-local state, you time evolve with a local Hamiltonian, you still get a pseudo-local state. So they are stable under time evolution. Contrary to Gibbs states, of course. You time evolve a Gibbs state for a finite time, there's no longer a Gibbs state in general. But they still take that form. They are still determined by pseudo-local charges. Okay? So, yeah, questions about that? So, with that family of states, one can go further, okay? And one can basically, well, this is not so complicated theorem, but it's something like a thermalization hypothesis. It's a stationary state thermalization hypothesis. If you do have a pseudo-local state, and that pseudo-local state is stationary with respect to the Hamiltonian, to some local Hamiltonian, then it must be a Gibbs state, as long as this Hamiltonian is completely mixing. Okay? It's like an ETH, right? You have a state, stationary, so here's not an eigenstate, a stationary state, which is of this pseudo-local form. Okay? And it's stationary with respect to Hamiltonian that is completely mixing. It doesn't have other conserved charges that, other than itself. Okay? Then this state must be thermal. Okay? So that's the thing. And the temperature is determined by these proportionality constants that occur in the statement of completely mixing. Okay, so pseudo-local states are quite nice. They have the nice properties. They connect to Gibbs states if you have completely mixing or not integrable Hamiltonian. Say. Questions about this? What more could I do with pseudo-local states? Well, one can define GGE with respect to these states, and that maybe makes it a bit clear what they actually are. Okay? So GGE is just a pseudolocal state which is stationary with respect to some local Hamiltonian. Local Hamiltonian being completely mixing or not, doesn't matter. Okay? So what does it mean? So if I reinterpret this whole thing in terms of a density matrix, what it would really mean is that the GGE density matrix is not just an exponential of some beta I, qi, or exponential of some pseudolocal charge. Is in general a path order exponential of an integral of a family of pseudolocal charge, conserved pseudolocal charge. In fact, it's a product of two path order exponential in the two directions. That's because that makes the whole thing nicer with respect to Hermitian properties. Okay? So path order exponential that goes in one direction, path order exponential that goes in the other direction. So if these Q are Hermitian, then this whole thing is Hermitian. So that formal definition of GGE comes back to this. Okay? Of course, this is, well, that precise definition of GGE comes back to this. This is a formal expression that doesn't really make sense because I've never defined pseudolocal charge as operators. Can exponentiate them. I don't know how to exponentiate them and all that. I define them as linear map on observables. But it comes back to that, yes.
Well, this proves then that the fact that these charges they are quasi-local.
So, so the quasi-local, or more precisely, the pseudolocal bit is important because there's a Hilbert space structure, and that's what allows you to. So it's a complete space. That's what allows you to take large time limit and make sure that you still get pseudolocal charge. The completeness of it. That's why you need pseudolocal. If you just start with local, it's not complete, so you lose it. That's the crucial.
I think he was asking why they are non-local.
Well, because in the end it comes back to this. If you take local there and take an infinite sum, it's not necessarily local. Local things they don't form a complete space. It takes some large time limit that converges in an appropriate way is no longer local. Right? But pseudolocal is complete, and that's why in the end you can take large time limit and you get pseudolocal and it's fine. That's why these pseudolocal states they are well behaved on the time evolution.
Sorry, can you show again the definition of omega subscript s? Sorry to make it shorter here. I didn't recall it, but basically, if omega is a pseudolocal state, right, then there's a flow. This omega s. So there's a flow. There's the flow associated to it. Right? So everywhere along the flow, you ask that these things are conserved by this H dynamics. Then this is GGE. Right? So this is kind of, in a sense, a bit better than the standard formulation because it does allow for the possibility of non-commuting flows. You can have conserved pseudolocal charge that are flow in different directions, but that don't necessarily commute. And here you usually assume they commute. And this non-commuting aspect was actually studied by Fagot 2014. So it is something that has been looked at. Yeah.
Why are you saying that you cannot include the non-commuting charges in the expression?
No, you can include them there for sure. Usually people think of them as commuting, but of course, it's not that this does work. But this kind of naturally takes into account the whole thing, yeah. Other questions?
I'm sorry, again, the initial state of this flow is what?
So this flow starts with the finite temperature state. This is how the betas being 0 in the formal, beta equals 0. So the flow, basically what is it? Is like rescale out your beta times s. Take s from 0 to 1. That's the flow. That would be an example of flow. But that's really precise.
Just to understand that you need this flow because it's a technical way to define this exponential.
Yeah. Let's put it that way. Yeah. So I don't know how else to define.
Right,
exactly.
It's to dynamics. It's just
No. It's not exactly. Yeah, good point. Sorry. So this flow is just a way to define the path order exponential. Path order exponential can be defined by derivative. dd s of u of s equals something times u of s.
So you can check this flow. I mean, write the equation for the charges. I don't know whatever.
This is just out complete general, right? So if you give me some GGE, then I can certainly construct a flow that will make it agree with that definition. Yes.
Do you have any clue under which condition the definitions they are the same? not very much. I mean, it depends, is this some, what's the locality properties of this? It's not completely. This is so very different context. Like this, I don't know exactly how to define that, but this I know how to define it. To connect them, the connection is really formal. To make it completely exact, this I don't know. But the idea is basically you put an S there, and if you differentiate with respect to S, you bring down this sum of beta IQI. If this is pseudo-local in some way, then you get a flow equation. That's basically the idea. But how to make that precise, and it's not so clear. Other questions? Yeah.
So I'm just behind the terminology. When you say non-commuting flows, are you saying that some of the QIs do not commute?
So that's more or less what I would say here. Yeah. But non-commuting flow, what I mean is flow is these are pseudo-local charges. I would say you go in some direction according to some pseudo-local charge, and in some other direction, and then back and back, or you do the opposite way, and you don't get to the same point. So I can make that more precise in terms of evolution with pseudo-local charge. Right?
So you really, so all the QIs commute with your Hamiltonian, but they do not necessarily commute.
That's correct. That's correct. Yeah, that's it. Okay, so that's the definition, and then with the definition you can prove something. And so here's a GGE, generalized thermalization theorem. If you do start with a pseudo-local state, any pseudo-local state, and you evolve with a Hamiltonian, local Hamiltonian, what you get in the end is a GGE under these conditions. Conditions are very similar to the ones before. You must have clustering even at large time in a uniform fashion, and you must have existence of these large time limits of a response function. Right? If you have that, then you do get a GGE according to my definition. Then you get a GGE. Okay? And you can start with any pseudo-local states, so give states or other GGEs if you wish. What is the whole family of pseudo-local states? I don't know. I just know some examples. I don't know. If you give me a state, is this a pseudo-local state? This I don't know. I'll say comments about that. Okay, so that's a generalized thermalization theorem. Any questions about it? Okay, so what is the main thing about the proof you were asking me? Why pseudo-local charge? So the main thing is that these pseudo-local charges have a very nice structure. In fact, the structure was already suggested by Rosen in 99. They have a Hilbert space structure. And the structure that Rosen suggested, I kind of myself transferred it, in fact, in terms of response or susceptibilities. And this what allowed me then to go a bit further. So what's the structure? Well, these susceptibilities give rise to a Hilbert space. Okay? So this, you can see that it's A comma B as an inner product between A and B. Okay? In fact, it's more precisely a semi-definite set-linear form. It has potentially a null space. You can take it away, and you can complete it, like in the Gelfand-Naimark-Siegel construction. You get a Hilbert space associated to that state, right? This inner product. And it turns out that the pseudo-local charges are in bijection, continuous bijection, with this Hilbert space. So for every pseudo-local charge, there's an A in that Hilbert space such that the action of that charge on anything is just the overlap between A and B. Okay? So there's a Hilbert space structure. So they are complete with respect to that structure. Okay? The opposite also holds. If you remember, for local charges, I was telling you, if you took the local charge, you directly get that. So this is just the extension of this local charge equation. And to extend it, well, you need to complete space, you need to fill this space. Okay. And then by these nice representation theorem, any pseudo-local charge can then be extended to a continuous linear function on that. More importantly, any continuous linear function on the Hilbert space is a pseudo-local charge. And this last bit is, of course, what allows me to prove this thermalization thing. So you go at large time, and you prove this is a continuous linear functional. And what you do, you just find what conditions will allow you to say that this is a continuous linear functional. What are the conditions? Well, these are clustering at large time, the existence of large time response function. These are conditions. These conditions tell you it's whatever you get is a continuous linear functional. Hence pseudo-local charge. Hence you have a state which looks like that. So this is the basic thing. Any questions? Okay, so I should probably finish soon. Now, what I wanted to say, the last bit is, basically this Hilbert space structure tells you you have a kind of infinite dimensional Riemann manifold where every local space has kind of has a Hilbert space structure, and you can perhaps study these quantum dynamics problem using this kind of a geometric description. Okay? Conclusion, well, this is a framework which is directly in the infinite volume limit for studying non-equilibrium quantum dynamics, especially the generalized Gibbs ensembles and generalized thermalization. So I do get precise theorems, precise definition of GGE and precise theorems about it. They are not so directly related to what people usually write as GGE, but they are related. Certainly, I mean, this is the intuition is the same, okay? And they include the pseudo-local charges in general. Okay? Now you can say what are these pseudo-local states? There may be a way of relating any state with particular Rényi entropy behavior to pseudo-local states. So the study of a connection between Rényi entropies and pseudo-local states might be very useful and might lead to an ETH theorem in some way. Okay? Connection with GG results, of course, a lot of nice GG results, especially that paper where explicitly the quasi-local charges were found. One question is, for instance, are these quasi-local charges a basis for the space of pseudo-local charge, which we know is a Hilbert space, so that way that will connect these results to my general theorems. And one can perhaps use similar techniques for other non-equivalent situations, such as energy transport and other things. Okay? Thank you for your attention.
We have already many questions at the top, but maybe a couple of them more. Yes.
So usually you start with KMS states when you are in thermal equilibrium. So can you say how the states which you arrive at, how they differ from these KMS?
Yeah, so actually,
a generalization of them?
Yeah, that's a good question. It's something I should have added as another point. Relation to KMS, I don't know. Indeed, in this quantum chain problem, I think you can show that these thermal states are unique thermal states, unique states satisfying the KMS relations. And so one can certainly ask a question about these GGEs. Do they satisfy some KMS relation? And it's a good question. I don't know the answer. Yeah.
Does the formalism you've developed give you a way to distinguish cases where you need quasi-local charges from when you don't?
I don't know how to distinguish these cases, indeed. Yeah.
There's no alternative signature you could say, no, I don't need these quasi-local charges for this case.
No, I don't. In my calculation, I didn't see any signature of that. But that's obviously a good question, because some cases you do. And I know in integrable models it's potentially related to the presence of strings and all that, so I don't know all the theory about this. But here, I cannot say more about it.
Yeah. I kind of lost how you pass from stationary state. You say that at the end of the state that you get must be stationary with respect to the Hamiltonian.
Yes.
How does this imply that it is a Gibbs state?
So in the case, I mean, this is very non-trivial that it implies a Gibbs state. It's a theorem, say. Okay? But so you use this definition. So what you say, you say last time limit exists and is stationary. That's one thing. So the whole flow is stationary. You can show that the whole flow is stationary. And then you say, well, at every point on the flow, you use this completely mixing condition. So what can this pseudo-local charge be? Because it be proportional to Hamiltonian. Okay? So the whole flow will be proportional to Hamiltonian with some proportionality constant. Then basically it's a Gibbs state. But there's some technical thing you have to make sure that what you get is really the Gibbs state, with a constant beta or some beta you can calculate and all that. So you need some elasticity properties.
But again, it's not trivial that the temperature is given by the conservation of the energy.
It's not trivial, no. Actually, in fact, the value of the temperature, I have a formal expression for it, and I don't know exactly what it would be. Supposedly it's given by the energy density. I can maybe prove that, But all I'm saying is there exists a temperature, supposedly higher temperature than the previous one. In fact, that's another good point. So, can you say something about entropy? Does entropy increase when you go from one state to another state under this infinite time evolution? Can you define entropy in some geometric fashion and show something about it? That's another question. Yeah.
Okay, some more questions? If not, let's take a break again.